So for the projection of two vectors, let's think in terms of an image like that, where you've got one horizontal vector, which we'll say is W, and another above it V, and you got a light shining down on it. And thinking of that, you would cast a shadow from V onto W, and that's where we get the idea of the projection, where in particular that's what's called the projection of V onto W, which we denote PROJ subscript WV. We are specifically looking at the projection from V onto W. And if we adjust this, we look at it a bit more broadly with our diagram and get a bit more notation into there, we can think about the relationships between our lengths and the angles between. And we will have that the angle in the middle there, theta, is such that cosine of that angle theta, I'm always getting ahead of myself, is going to be equal to the magnitude of the projection divided by the magnitude of V. That is, it's going to be adjacent, the projection, over hypotenuse, the magnitude of our vector V. And from there, if we want to get a better description of what's going on in terms of that projection, we can pull these terms around and get that the magnitude of our projection of V onto W, which is not the nicest notation to write by hand, but so it goes, that will be equal to the magnitude of V times cosine. And from there, well, we have that cosine of that angle theta can be described in terms of the dot product like we did before. That is, we will have the magnitude of V times the dot product of V and W divided by the magnitude of V times the magnitude of W. And the nice thing about magnitudes is that even though we have lots of notation in there, really, we should remember that this is just a number. And if you've got just a number over just another number, they'll cancel out. And what we'll be left with is that the magnitude of our projection is equal to the dot product V dot W divided by the magnitude of W. So we're most of the way there in terms of being able to describe what that projection acts like, because we can say how long the projection is. And then from there, if we want to be able to actually describe the projection itself, we should think back to something we saw last week, which was the idea of a unit vector. And the thing about a unit vector is it is specifically designed to capture a direction without affecting the magnitude, because it should have a magnitude of 1. Where in this case, based on how we have this set up, the projection is always going to be in the same direction as the vector it is being projected onto, as it were. So the projection is always going to have the same direction as W. And if we want to capture that direction as well as the magnitude, that is, describe the projection of V onto W, we just need to get the magnitude of that projection, which is V dot W divided by the magnitude of W times the direction that the projection goes in. Where here, we can do that in terms of a unit vector for W to represent the direction. So we'll multiply this times W over the magnitude of W, where what we'll get, merging our terms together, is V dot W over the magnitude of W squared, and then it's kind of clunky looking, but we'll have an extra V hanging off on the end there, describe our projection. And to see what this actually looks like, we're going to get an example. So for this example, we want to find the projection of v onto w for vectors v equals 2i plus 4j and w equals negative 2i plus 6j, where in this case we've got a diagram like so that we can work with. And what we should understand here is this looks weird, but you should be careful to note that the dot product always gives us a number, and the magnitude is always itself a scalar number. So even though it looks like we might be multiplying like some kind of vector thing times a vector without being careful about our notation, bear in mind this mess of things is always going to end up being a scalar. It's not always going to be a nice scalar because you've got some square roots in there that you're chasing around, but it is always just a single scaling term that we're multiplying a vector by. Because we're always going to be describing the projection, at least in this way, as a vector. You can talk about something else with projections, but we're not going to worry too much about that. Anyway, in this case, we just need to find our pieces to get that projection. We have that the projection of v onto w is described by the dot product, v dot w, over the magnitude of w, let me be careful, squared. So actually that does make our terms a little bit nicer, because we don't have as many square roots to chase around when we're explicitly getting rid of them. But we got that, and we're going to multiply it by the vector w that has too long of an arrow in this case, but that's okay. Hopefully by now we're somewhat comfortable with the idea of working with a dot product. Here we will end up getting 2 times negative 2 plus 4 times 6 divided by negative 2 squared plus 6 squared multiplied by the vector negative 2i plus 6j. And once we have all of our terms like that, we'll pull these together. It's multiplication and addition. Hopefully we're somewhat comfortable with that. We should get 20 divided by, in this case, that's going to be 4 plus 36, or 40. So we get 20 over 40 multiplied by our vector, negative 2i plus 6j, where, like I said, this value is always going to end up just being a fraction. It's just, well, not a fraction necessarily, but it's just going to end up being a scalar, a number that is. So we will end up with, in this case, negative I plus 3j. And from here, we can talk about taking our projection and using it to break down our vectors like v into 2 parts. That is, we can look at a concept called a decomposition. And that's what we'll see next.